And his title, as you can see there, is a secondary pairing between K-theory and K-homology. His profile.
Okay, thank you very much, Willie. Thank you very much for the invitation. That's good to be here. I'm actually in Dresden right now, visiting Andreas Tom, and I also should thank Vadim Alexeyev, who's just in the background, for use of his office during this talk. So much appreciated. Hopefully this goes okay. I'm not used to both Vadim's computer and Google Meet, but hopefully it goes all right. So I'm going to talk about something which is fairly classical, and there are serious hints of much of what I'm going to talk about in the work of Brown, Douglas, and Fillmore setting up K-homology the first time around in the mid-70s. Not so much in what Kasparov was doing at the time, particularly in a lot of the articles that Larry Brown was writing, which never really had the details fleshed out fully for reasons I'm not honestly completely sure about. But anyway, that's the starting point. Okay, there we go. So plan for what I will talk about is I'll start in generalities. The talk is about topological K-theory of C-star algebras, and for that first section, I'll just be talking. Can you see my cursor, by the way, on the screen if I circle things? Okay. So for the first part of the talk, I'll be talking about general theory. Everything will be for a general separable unital C-star algebra. Don't really need unital, that's just being lazy. Then I will connect to flat bundles. So in the sense of the Atiyah-Patodi-Singer completion theorem, although that will not make a specific appearance, but the idea of relating finite dimensional representations of a group to flat bundles, flat vector bundles over its classifying space. That will be part 2, and I will connect that to the stuff I spoke about in the first part a little bit, and the Bamcon conjecture. There's a lot of things there that I don't understand still. I think there are topological questions that are interesting, but which seem to be quite open. And then in the last part, I'll talk about how to actually compute for secondary pairings that I introduce in the first part. So that will be about relative eta invariants, which were introduced, again, in the mid-70s, completely independently of the other stuff I'm talking about by Atiyah-Patodi-Singer. So the last part is in the spirit of index theory. The motivation for everything I'm talking about is coming from approximate, the theory of approximate representations of discrete groups. I will not say too much about that, but that's in the background. Partly what was going on with the paper that underlies this talk is I wrote my original paper on this stuff, which is long, in a way which was quite suboptimal with hindsight. And this is an effort to put some of the machinery in that paper in its proper context, but also hopefully in a way which will be useful for other things. Which, yeah, I'm starting to see that a little bit already, but that's where we're going anyway. So, generalities. Part 1, general theory. So A for this part is going to be a separable unital C-star algebra, and I'll be talking about its topological K-theory and K-homology groups, also its KK theory groups. So upper superscript I for the K-homology of a C-star algebra. There's essentially only 2 K-homology groups by Bott periodicity, so I is 0, I equals 1. And I won't really need to do this, but think of them as the KK groups, where you have A in the first variable and C in the second variable in the sense of Kasparov. Although I will be, again, what I'm talking about is more in the spirit of Brown, Douglas, Fillmore theory. Now, originally defined by Brown, Douglas, and Fillmore in the mid-70s, but not so much exploited by them. These groups come with a canonical topology that was studied by quite a few people in the interim. Should probably mention Norberto Salinas and Claude Choquet particularly. The final form, the definitive form, which works in general, is due to Marius Darlat and Mihai Pimsner, or more precisely, what I'm going to say is in a paper of Marius Dardelat, but he attributes the idea to Mihai Pimsner, who I think was already quite sick by the time this was written down. But this is the definition. The topology is determined. It's a first countable topology, and this is determined by stipulating that a sequence xn converges to a point x infinity if and only if there is a class x, which I've lost my mouse, never mind. There's a class x in KK theory with a in the first variable and the one-point compactification of the natural numbers. So that's this n plus is the one-point compactification of the natural numbers. So if you have this KK group, because KK theory is covariantly functorial in the second variable, there are evaluation homomorphisms for each integer and the point infinity. And convergence in the KK groups just means that, or in K-homology in this case, special case, just means that you have a class in this KK group with continuous functions on a one-point compactification, the second variable, which evaluates to the various things in the sequence and the limit point. Okay?
Sorry to interrupt. So if you have a B, if you have a second separable sister algebra B, and you could put B tensor.
You could.
Yes. Okay, so that's a general fact.
You could and should, yes.
So, okay, so in particular, usual K-theory also has topology.
It does, but it would be discrete always. This is only interesting for KK theory or K-homology. If it's KKC, B, this reduces to the discrete topology. You don't get anything interesting out of it. It's only interesting if you have something non-trivial in the first variable.
Is C of n plus isomorphic to something in KK, like, I don't know, a sum of copies of C?
It's the one-point compactification or the unitization of a direct sum of countably many copies of C.
Okay.
Yeah. So it's that, but compactified. Yeah. Exactly. Yeah. So that's it. This topology is discrete whenever the KK groups are countable. So it's not interesting when the KK groups are countable. But K-homology, and therefore K-theory groups for a separable C-star algebra are always countable, so you don't get anything interesting. However, K-homology groups for a separable C-star algebra can be uncountable, and this topology can be non-trivial. If they're countable, it's just, again, discrete, and you don't have to worry about it, but for correct level of generality for what I'm talking about, I will need it. So I will be treating that topology. An annoying fact about this topology is when it's non-trivial, it does not have to be Hausdorff. So the actual object I'll be working with is this, I've lost my mouse again, there we go, is this KL group at the bottom, which was initially defined by Mikhail Rodam in the presence of the UCT, and then by Marius Dardelat, also Huaxian Lin had something similar in general. So this maximal Hausdorff quotient group, you just take the trivial subgroup, you take its closure, and if you've got any topological group, that will always be the maximal Hausdorff quotient group. That will always be a normal subgroup, and this will always be the maximal Hausdorff quotient group. Again, if the K-homology group happens to be countable, you're not doing anything. This just gives you K-homology back. But in general, I will want to do this to avoid certain pathologies. And also, is this, for the applications I want, this is the more interesting object. The closure of 0 is unimportant for what I want to talk about. Okay, so that's KL theory. I think it's called KL theory because L is the letter in the alphabet after K, but I might be wrong.
So, I mean, you say that for your applications, the abstraction to Hausdorffness is not important.
Yes.
So,
yeah.
All this fad of caring about non-Hausdorff things, which is in a different context, say in group points.
Yes.
Now,
yeah.
So this doesn't affect here. So it's not like tomorrow somebody's going to come and say that, well, we have to study this precise.
Yeah, for what I'm going to talk about, all the operations I'm talking about are continuous, and they don't see zero, therefore they don't see the closure of zero either. So quotienting out by the closure of zero is the right thing to do. Just get rid of it. For other applications, the closure of zero is probably very important. I'm working on that in a completely different context for other reasons, but yeah, that's for today's talk not important, and it's just not the right thing for. Yeah, you may as well just get rid of it. It makes life much simpler. It has getting rid of it has other complications, which I'll maybe say a bit more about later, but anyway, that's a good thing to do for current purposes. The topology, by the way, is not a particularly nice topology. It's, well, it's in a way, it's quite simple. It's always totally disconnected. You can exactly classify which topological spaces can occur. It can basically be discrete, or a Cantor set, or a Cantor set cross discrete, or an infinite product of copies of the natural numbers, and that's it. My students worked that out. So not so bad. Okay, so the motivating problem is you want to understand you have two classes in KL homology, or K homology, but KL homology, and you want to understand when they're the same, which in general is difficult because K homology is hard to compute. And the key tool for telling when classes in K-homology is the same is to compare them with K-theory, because K-theory is easier to compute. Topological K-theory of C-star algebras is easier to compute than K-homology. And so you have a pairing between this thing is the IF-K homology group, that thing is the IF-KL homology group, and just by the Kasparov product, or the way these things are defined, they will pair with one another in a nice way. Now, because that pairing is valued in the integers, it will automatically always lose information. It will, for example, always kill the torsion subgroup of KL if there is a torsion subgroup, and in general, it will kill more things. So my goal is to define a secondary pairing which detects the stuff I'm going to call little KL. That's the things that the primary pairing does not see. And I want a secondary pairing which will detect all the elements of that, and therefore will give me complete information about the capital KL groups in terms of the primary pairing and the secondary pairing in good situations. This is very much in the spirit of, oh gosh, I've forgotten the name. I think Morgan and Sullivan work on homology with finite coefficients in the late 70s. I might have got the first name wrong. It's an M name, but maybe wrong. Anyway, okay. So here's the construction of the secondary pairing. There's about 3 different ways to do this, and the first part of the paper I wrote about this is doing those and proving they're all the same. But there's several different ways you can reasonably do this. So this is probably the simplest one. Take Q to be the limit of the directed system of matrix algebras, where you just include the matrix algebras in each other unitly, where n divides m. So you can just include mn of c and mm of c in that situation by just putting them down the diagonal as blocks. So that's the universal UHF algebra, as it's called. And it has the property that the K-theory of A tensor Q is the K-theory of A tensor Q for rational numbers. Easy to see. The other thing I'll need is I'll take the unit inclusion into Q, and then this C of iota will be the mapping cone of that thing. Okay, so the mapping cone is the functions from the half-open interval, which vanish at 0, and the value at 1 is just contained in the scalar multiples of the unit in this case. That contains the suspension of Q. That's just the stuff which vanishes at both ends on the interval as an ideal. And tensoring that ideal in the mapping cone by A, I get a short exact sequence like this. And therefore a long exact sequence, or more precisely a 6-term exact sequence, but I didn't fit it on this slide, like this thing at the bottom. Okay, in topological K-theory of C-star algebras. Now, you can split that up into 2 short exact sequences, because the maps from K-theory of A to K-theory of A tensor Q are exactly what you think they are. They're just map K-theory to itself tensor 1 in Q, as you can compute. So if you split this up by taking co-kernels and kernels, you get the following short exact sequence on the top. So the co-kernel of that map is this, and the kernel is just the torsion subgroup of K-theory. And if we've got an element X in our little KL group, that's the stuff which vanishes on the primary pairing with K-theory, then I get a picture like this. I've got the map induced by X going from Ki of A to, well, Z, K naught of the complex numbers. That one's just 0 because X is in little KL. Its primary pairing vanishes by definition. Then I've got another one which just goes to the K-theory of the mapping cone, which is Q mod C. That's straightforward to compute from the mapping cone's sequence. And then over on the right-hand side, I've got the torsion subgroup of K of A, but in the opposite degree from the one I started with. Torsion subgroup of K1, that's 0. And because this map on the left is 0, this map in the middle descends to the quotient, which is this torsion subgroup. So we get this dashed arrow from the torsion subgroup of Ki plus 1 to this copy of Q mod C. Okay, by the first isomorphism theorem, that's simple algebra. And that's our secondary pairing. So given your element in the KL homology of A, the little KL homology, the stuff where the primary pairing vanishes, that pairs with the torsion subgroup in the opposite degree, which I'll sometimes abbreviate as little t, Ki plus 1 of A. And that pairing lives in the group of roots of unity, the rational numbers modulo the integers. Okay, so that's the construction of the secondary pairing as I'll use for this talk. So nothing particularly complicated. Okay, so theorem, just here's the structure of this thing. There is a natural commutative diagram of exact sequences. So on the top, this is more or less by definition of big KL and little KL. Big KL has a pairing map to Hom K-theory Z. Little KL is the kernel. And then on the bottom, I've got various other Hom groups. So the same Hom group on the right. In the middle, I've got the Hom groups of total K-theory. So what that means is you take K-theory and you take K-theory with also all possible finite coefficients, finite cyclic coefficients. So you take all of those groups. That's a module over the Bockstein category, the category of natural transformations between those various finite cyclic coefficient groups. And so treating K-theory with all the finite coefficients as a module over that category, it makes sense to talk about the Hom groups from total K-theory, this thing, to total K-theory of the complex numbers, which I'll just write as Z underline. And you get this map in the middle, which is after Maria Stadler and Terry Loring. And then this map delta is the secondary pairing that we just constructed. You can compute that the kernel of the map from the homomorphisms in the Bockstein category to the standard abelian group homomorphisms is exactly the homomorphisms from the torsion subgroup in the opposite degree to Q mod C. That's a computation you can do. So you get this short exact sequence at the bottom. The natural map from Hom lambda to Hom is just forget all the finite coefficients. So you can kind of compile those into this Hom group on the left. Okay, by, again, a little bit of algebraic messing around, taking lots of direct limits and inverse limits and things like that. Moreover, if A is nice, if it satisfies the universal coefficient theorem of Rosenberg-Schockert, so in particular if it's commutative, which is the main case I care about, or if it's a group C-star algebra that satisfies the Baum-Kohn conjecture, it's the other case I care about, strong enough form of the Baum-Kohn conjecture, then the vertical maps are all isomorphisms. In particular, that forces the top sequence to be exact, which probably isn't true in general, although I don't know a counterexample. And the secondary pairing on the left, it's not just an isomorphism, it's a topological isomorphism, where the bottom group has the topology of pointwise convergence. Same thing for the one in the middle, that also becomes an topological isomorphism. And that vertical map on the left, the secondary pairing, becomes a topological isomorphism between little kl and the Pontryagin dual of the torsion subgroup of K-theory in the opposite degree. Now, the Pontryagin dual, naturally, it's defined to be homomorphisms from an abelian group to the circle group. But if you're looking at a torsion abelian group, then if you will actually, any homomorphism to the circle will actually take values in the torsion subgroup of the circle, or in other words, the group Q mod C of roots of unity. So you do get exactly the Pontryagin dual, and the topologies also match up. The topology is the topology of pointwise convergence, so you can check that that all works and behaves itself properly. Okay. So the upshot from all of that is that if you've got a class in KL theory, and you know, or you've got two classes in KL theory, if you know they agree on the primary pairings, then their difference has to live in this little KL group. And if you also know that all the secondary pairings agree, then you know they're the same class. And that's what I would want to know for the applications I have in mind. Okay. So that is the end of part 1. Any questions about that? Cool. If not, I will move on.
I just remark that the construction is simple and seems that could be. So when I read the introduction, I thought it was the main theorem to show that delta was an isomorphism, but you didn't make it look like that. Right?
No, it's not. Well,
maybe the fact that it matches up with all the topologies.
The fact it matches up with all the topologies and it matches up with these usual pairings is a bit of a pain to actually prove. If I'm underselling it, maybe. At least for me, it did take some work to prove that. Yeah, and also just to compute this short exact sequence at the bottom, that also takes a bit of work because the kernel was previously not known, it seems, so no one had computed that properly. So a bit of work to do there, but no, I wouldn't say anything is particularly deep. Yeah.
So, despite of your being American citizen, you keep the British under.
Yeah. I mean, I haven't.
Okay.
Yes. Yeah. No, I've tried not to adapt American bombast, although that is the current fashion, I guess. But anyway, yeah. Part 2. All right, so flat bundles. How does this relate to flat bundles? So now we're going to switch topics a bit. I'm going to take countable gamma as a countable torsion-free group. It will fairly shortly be amenable or AT-amenable more generally. And I'll take C star gamma to be its maximal group C star algebra. Not the reduced one is the more common one used, but I'll take the maximal one. So that's just the completion of the complex group algebra for the supremum over all norms induced on that coming from unitary representations of the group. So that's a nice C-star algebra, in general quite hard to understand, but it needs to be a nice C-star algebra. And B gamma I'll take to be a CW module for the classifying, CW model, sorry, for the classifying space in the usual sense. Then way back in the mid-70s, 1975, first paper on this, before the Bamcon conjecture, Kasparov introduced both assembly and co-assembly maps going between the K-theories and K-homologies of the classifying space and the K-homologies and K-theories of the group C-star algebra. So the co-assembly map, Kasparov did not set it up like this because he didn't know what KL homology was at the time. He just used honest K-homology. But if you set it up using KL homology, what it ends up doing is it's a map from the KL homology of this group C-star algebra to the inverse limit of the K-theories, so upper star now K-theories, it's contravariant in spaces, of all finite CW subcomplexes of B gamma. So those naturally form an inverse system because K-theory of spaces is contravariantly functorial. So you get an inverse limit of those K-theory groups. This is very much what Atiyah does, which was one of Kasparov's big motivations, but this is very much what Atiyah does in his paper Characters and Cohomology of Finite Groups. He takes the classifying space of a finite group, which is an infinite CW complex, and takes the inverse limit of the K-theories of the finite subcomplexes.
Are you saying this map is continuous?
Not yet, but yes. It is continuous. Yeah, and that's effectively what it means, that the image lies in this inverse limit over all finite subcomplexes. So if you put the inverse limit topology on the right-hand side, this map will be continuous. Yeah, that's again another reason for using the topologies everywhere. I'll say a bit more about that on the next slide. The way this is defined, by the way, is you build this thing M gamma, which is called the Mashenko bundle. So you take E gamma, the universal cover of the classifying space, and you take the balance product of that with C star gamma, where gamma is acting on the left on C star gamma by left multiplication. So it's an automorphism of C star gamma considered as a right module over itself. And gamma is acting on the universal cover of B gamma by deck transformations. You restrict this Mashenko bundle to a finite subcomplex. That gives you a sequence of maps, collection of maps into the K-theories of those finite subcomplexes. They're compatible, so they fit together to give you a map into the direct limit. And that's
so you're mixing, you're putting together a space and an algebra. Of course, it's a non-algebra, so it has a topology. But so is that?
Yeah, I mean, it would probably be more natural to. This is the bundle. It would probably be more natural to look at the module of sections, which is a finitely generated projective module over C of B gamma tensor C star gamma. That's probably the right. That's a lie. That's exactly why you need the limit, because it's not a module over that. It's a module. If you restrict it to a finite subcomplex, it becomes a finitely generated projective module over C of Y tensor C star gamma. So you need to restrict to the finite subcomplexes to avoid nasty topological issues. But yeah, that's probably the more natural thing to do. That's also what Gennady actually does in his paper. And thought of like that, it's an element in the K-theory, so the KK theory of C, comma, C of Y tensor C star gamma, and therefore it gives you by Kasparov product a map like this. So that's how it works, just Kasparov product with that thing. It's the easy version of the assembly map. Okay, so now let's take a finite dimensional representation. So in other words, a finite dimensional unitary representation of the group. And that gives you a flat bundle E pi over B gamma, just by taking again the balance product with via the pi action on Cn. And the way that the Mashenko bundle is defined, if you take the assembly map image of this of pi under the assembly map, then it just takes the tensor product of the Mashenko bundle over pi, considered, which is making Cn into a C star gamma module, and you get exactly E pi. So the co-assembly map, which again, this is Atiyah from his paper Characters and Cohomology of Finite Groups, is what Kasparov was trying to generalize. This is what Atiyah did for finite groups. Kasparov now did it in general for possibly infinite groups. So the co-assembly map takes finite representations to flat bundles. All right. So if we have an AT minimal group, also torsion-free, then, so this is essentially the seminal work of Higgs and Kasparov on the Baum-Kohn conjecture. It also proves this, which is not explicitly in their paper, but the methods can be used to deduce this. So you get isomorphisms between the KL homology of C star gamma and this inverse limit of K-theories of finite complexes of the classifying spaces. That's a topological isomorphism. And on the left-hand side, you've got the stuff the primary pairing doesn't see as a subgroup. That's actually the maximal compact subgroup as it happens in this setting of that topological group. and the co-assembly map restricts to an isomorphism of that with the inverse limit of the torsion subgroups of those K-theory groups. Now, because it's the K-theory of a finite complex, it's finitely generated, so its torsion subgroup is finite, so this inverse limit is an inverse limit of finite groups, so it's a nice, compact, totally disconnected group. And that is partly why I know that the left-hand side is the maximal compact subgroup. I would conjecture that happens in general, but I can't prove it in general. Yeah, anyway.
One question. The fact that you added torsion free
yeah.
afterwards.
No, I didn't add it afterwards. That's a reminder. I had it as a standing assumption at the start.
Okay, but this made me wonder whether you have a result that applied to more general groups, but was too complicated to state.
I don't, but I suspect there is. So there are some partial results along these lines by Schmuel, Weinberger, Junxiao Wu, and Guliang Yu, which allow for torsion subgroups which possibly have torsion, but they rationalize everything. They tensor everything by Q, and my whole point in this talk is to deal with torsion subgroups in a way. So I don't, for what they do would not be useful. There probably is a general theorem which works for non-torsion free things, but I don't know what it is. You would have to, instead of working with B gamma, you would have to work with the equivariance K-theory of E bar gamma of the universal classifying space for proper actions, not proper and free actions.
Yeah.
So, and I suspect that's doable, but I haven't tried to do it yet. But it's an interesting problem. I would hope someone does it eventually and gets the proper theorem in full generality.
Once you wrote that you took the maximal sister algebra, I expected some E theory would appear.
Yeah, if I were in the AT-amenable case, it doesn't make any difference because
of course.
Yeah. But you're if I were really pushing this to maximal generality beyond the AT-amenable case, I should be using E theory, yeah. And you can do the same thing.
But if you're AT-amenability, okay. So AT-amenability is more than amenability, and that's
bigger than amenability.
It's a larger class. That's what I meant.
Yeah, larger class. Yeah, exactly. Yeah, it's a lesser assumption. Yeah.
And I don't understand the corollary because you say, if these two representations are such that the difference is in KL.
No, sorry, this is misleadingly worded. It should say if. It should be read as saying if pi and sigma are finite dimensional representations of the same dimension, then the class of pi minus the class of sigma is in little KL0. So the class of pi minus the class of sigma is automatically in K-homology. K-homology is generalized homomorphisms from C star gamma to the complex numbers. So homomorphisms from C star gamma to matrices certainly make sense. But the content is that this class is actually in little KL, not big KL. It's in little KL under those assumptions. It's not in little KL if the group happened to be property T. So I really do need AT-amenability. I need the full force of the Baum-Kohn conjecture for that.
And as you said, K-homology are generalized homomorphisms from the algebra to the complex numbers. Right?
Yeah.
But there might be, the K-homology may not vanish, so that generalized homomorphisms might exist. And yet, actual homomorphisms may not exist. A group could have no finite dimensional representation. So
that's right.
In that case, you just the corollary doesn't apply.
The corollary doesn't apply. Yeah. I'm interested
but
mainly.
But the theorem makes sense anyway.
Yeah.
Or is I mean, does an AT-amenable group always have finite dimensional representations?
No, definitely not. You can have simple simple infinite AT-amenable groups, for example. That's even simple infinite amenable groups. Nowadays, people know how to construct such things. So, and they wouldn't, finitely generated, they wouldn't have finite dimensional representations at all. So, yeah, that would, you definitely do not have to have finite dimensional representations. I mean, I'm using the theorem to, it seems like it's going to be massive overkill, but I'm using the theorem to get information about finite dimensional representations. That's actually what the process is here. I care about applications to finite dimensional representations, which is, so it's that way round. Yeah. And again, the reason that this is true living in KL is that the corresponding flat bundles, the difference of the flat bundles are torsion classes because they're flat bundles. So the Chern, you can compute the Chern character using connections via Chern-Bay theory, and that has to vanish rationally. So therefore, because it's an isomorphism, the difference has to be in the torsion subgroup of K-theory. That's roughly the argument.
There are these Giger-Simons classes.
Yeah.
Or flat bundles. Do they show up in this connection?
Yes, they are very closely related to the relative theta invariants, which will appear in just a moment.
Okay. I only mentioned go on. Okay, sorry.
Yeah, no, that's good. You're ahead of me. Yeah, they do, although I didn't fully flesh that out. But yes, I think you could probably express the things I express in terms of relative theta invariants more or less in terms of those as well. Okay. So part 3, the last 10-ish minutes, I'll just connect this to relative theta invariants. So to reiterate, we've got our formal difference of representations defining a class in little KL theory. And I would like to, for reasons I didn't really explain in this talk, but for other reasons, which I think are good ones, I would like to compute its pairing with the torsion subgroup of the K1 group of the maximal C-star algebra. Now, under these assumptions that the group is AT-amenable, which I need, any elements, we have a strong form of the Baum-Kohn conjecture, so any element of K1 of the C-star algebra can be represented by the image of a Baum-Douglas class. You can realize all of K-homology of the classifying space by these Baum-Douglas cycles. This is a cobordism type theory. So you have triples consisting of a closed odd-dimensional Riemannian manifold, possibly disconnected and possibly with connected components of different dimensions, but all odd. Then over that you have a Clifford bundle. That's a bundle with an action of an appropriate Clifford algebra. The Clifford, more precisely, of the bundle of Clifford algebras of the tangent space of the manifold. It's Riemannian, so that makes sense. It has an inner product on each tangent space. And then you have F, which is a continuous map from the manifold to B gamma. And triples like that represent classes in K-homology, and with the appropriate equivalence relation, they are exactly a model for K-homology. Important here, I am using that the group is torsion-free. I wouldn't know how to do what I'm about to do if it wasn't. But that's probably just a failure of imagination on my part. I suspect it's possible. I just don't know how to do it personally. Okay, so you take the image of such a thing in K-homology, and any class in K-theory of the group C-star algebra can be represented by the image of such a thing under the Kasparov assembly map, dual to the co-assembly map we had earlier. What I'm calling K1 homology is probably more often or often called RK1 homology, representable K-homology. It's the direct limit this time of the K-homology groups of finite subcomplexes.
If it is homology, shouldn't the I be an upper script?
I put it upper if it's a C-star algebra and lower if it's a space.
Oh, okay.
Because it's covariant for spaces and contravariant. Yeah, sorry. I don't know who did that first, but it's become a fairly standard convention. Yeah, and I think in the early papers of Kasparov, it's the other way around. In the later papers, it's this way around. it's confusing, unhelpful, but yeah. Okay, yeah, so this one is K-homology, this one is K-theory, because one's space, one's a C-star algebra. Okay, now if you've got a torsion class in the K-homology group of B gamma, and I pair that, the image of it under assembly with this class in the KL homology group of the C-star algebra, because the co-assembly and assembly maps are dual to each other, I can move this beta over to the left, and it's now the co-assembly map applied to this difference of finite dimensional representations. And what we said earlier, that image is the difference of flat bundles. And now I'm looking at something topological. I'm looking at the pairing between these difference of flat bundles and this Baum-Douglas cycle consisting of a manifold, a Clifford bundle, and a map to B gamma. Okay. Right. Theorem. And this is, mainly, I should say mainly, sorry, weird typo. So this is mainly due to Higson and Rowe and Nigel Higson and John Rowe, Paolo Antonini, Sarah Azzali, and George Skandalis. I'm using their work a lot, although there is still more to do, particularly in the difference between the rational and real numbers. That's a real pain in this context. But the pairing between this flat formal difference of flat bundles and this Baum-Douglas cycle is the so-called relative eta invariant of Atiyah-Patodi-Singer, which I'll explain on the next slide. So this secondary pairing is computed in terms of this index theoretic invariant defined by Atiyah-Patodi-Singer in the mid-1970s. So let me explain what that is.
One thing. So the difference is torsion, but each individual is not, right?
Yes.
So you cannot use bilinearity.
Yes. Yes.
Okay.
Yeah. Yeah, but the individual things only have they're only non-torsion as far as reduced. If I was working in reduced K-theory, they'd be torsion, and maybe that would be a cleaner way of setting it up, but yeah, not super important. Okay, so how do you define it? I'm just going to do this very quickly to get a sense of what it is. It's something that's defined very analytically. So you take your Clifford bundle, you can assign a Dirac type operator to that in a way which is independent of that's a choice of connection, but that's not important. Then you take that Dirac operator and you have it act on S, tensored by the pullbacks of E pi and E sigma. So F is a map to B gamma. You pull back those bundles to the manifold M. You then define an eta function by adding up all the eigenvalues of the operator, taking the absolute value of the eigenvalue to the power of minus z, multiplying that by the sign. That converges if the real part of z is larger than about the dimension is good enough. Because the eigenvalues grow like a polynomial in the dimension by the, Weyl asymptotic formula. And then the big theorem to make this well defined is that this eta function, as it's called, meromorphically continues to a complex plane and is regular at z equals 0. That's really hard to prove, and the way you prove it is using K-theory. You show that the residue class at 0 is a well-defined map on K-theory, and you prove it vanishes on all the K-theory groups, all the K-theory classes. So that's enough.
When you say you prove it, you mean you are citing?
Atiyah-Patodi-Singer prove it, yeah.
Okay.
In their original papers, yes. That's how they prove it. They prove it vanishes on generators. I did not prove that. Anything involving analytic continuation, I am unlikely to have been involved in proving it. This is not not mathematics I know very well. But yeah, hard and beautiful theorem, very analytic. Okay, and then your relative eta invariance is basically the difference between the values of these eta functions at 0, except you have to correct by something involving the kernels of the operators as well. But basically, it's the difference between these two eta invariants. Morally speaking, if you think about what happens when you plug in z is 0 into this equation, you're adding up all the negative eigenvalues with a minus sign, and all the positive eigenvalues with a plus sign, just multiplied by 1 in each case. So it's sort of like the number of positive eigenvalues minus the number of negative eigenvalues, which is infinity minus infinity, so it doesn't make sense, but you should think of it as a regularization of the number of positive eigenvalues minus the number of negative eigenvalues. That's what it's meant to measure, the spectral asymmetry of these Dirac operators. Okay. Very quick example. This is the basic example, easiest one. So M is the circle, the Clifford bundle is the trivial bundle, and the Dirac operator is d by dx times minus I. One of my representations is the character associated to a number theta, and the other one is the trivial representation. And Atiyah-Patodi-Singer compute that their relative theta invariant is exactly the number theta. Up to me getting the normalization. I should probably put a plus or minus there, because I think I might have got the sign wrong looking at this, but anyway, not important. This is a bit different to the cases in which I'm applying the theorem, because this relative theta invariant can take any value in R mod Z, not just in Q mod Z. And that's because the corresponding class that I'm implicitly pairing with is not a torsion class. It's the generator of the K-homology of the circle, which is BZ in this case. The other thing which is different about it is that it depends, E pi and E gamma, E sigma in this case, they're flat bundles, and they're different as flat bundles, but they're not different as topological vector bundles. They are the same topological vector bundle. They are both the trivial vector bundle. There are no non-trivial vector bundles over the circle. So they're both the trivial vector bundle, and this pairing depends on their classes as flat bundles. They are not isomorphic as flat bundles. However, in the theorem, this secondary pairing only depends on the classes as flat bundles. So it's a topological invariant. Not a geometric one. The structure as flat bundles is much more sophisticated geometric structure. Only depends on the classes of these things as flat bundles, which is a little mysterious, to be honest, but that's a consequence of the theorem. Mysterious to me, at least. Proper topologists might be able to explain it. Okay, so I'll just finish with a corollary, which I'll keep vague as to, again, my exact motivations. I've been going about 50 minutes, so I should probably stop. But corollary, I have a few proofs of this, but for the full version, I need the machinery developed in the previous slides. So assume that the dimension of B gamma is at most 3. So say it's an aspherical free manifold, which is the case I was mainly interested in. And you have an AT-amenable group, which is automatic if it's a fundamental group of an aspherical free manifold, and it's automatically torsion free in that case as well. Then if you've got any element x in the little KL group of the group C star algebra, then you can approximate, it's a topological group, but you can approximate it arbitrarily well by a difference of classes which are coming from one-dimensional representations. You can assume the second one is a trivial representation, in fact, so really just a single one-dimensional representation. And then that plays into theorems and representation stability that I wanted this for applications for. So final question, which I don't know the answer to, and I don't think anyone knows the answer to as far as I'm aware, but is this true without the dimension assumptions? So in other words, if you don't assume the dimension of B gamma is at most 3, can you write any class, there won't be one-dimensional representations before, but can you write any class in KL0 as a formal difference of finite dimensional representations? The answer has got to be no, because there have got to be AT-amenable groups which don't admit any finite dimensional representations but still have torsion classes in K-homology, but that seems to be open. And the same question is, which again seems to be something that topologists have thought about a bit, if I take this inverse limit of torsion subgroups of K0 groups over finite subcomplex of the classifying space, are classes of this form, which come from formal differences of flat bundles, are those dense in that K-theory group of the classifying space? Or maybe just assume the classifying space is finite, and then are they everything? This is a, you can think of this as a baby version of the Atiyah-Patodi-Singer completion theorem. So Atiyah proved, amongst other things, in his paper Characters and Cohomology of Finite Groups, that the answer to this question, which makes sense if the group is not torsion-free, the answer to this question is yes, if gamma is finite. That's one of the main consequences of what Atiyah proved in Characters and Cohomology of Finite Groups. But you can ask it for general, completely general groups, and it seems to be an open question. And then the Atiyah-Patodi-Singer completion theorem was a more conceptual approach later in joint work with Segal, which also treats compact groups, though that's a bit orthogonal to the case I'm thinking about here, which is for discrete groups. So it's can be thought of as a kind of weak version of the Atiyah-Singer completion theorem, but for infinite rather than compact groups. And I would be very interested in any progress on that. If anyone has anything to say, but I have no more to say, and I'm out of time, I think. So thanks for your attention. Stop now.
Thanks very much, Rufus, for the wonderful talk. I didn't understand the connection between this corollary on this slide and the theorem on the previous.
Yeah, you have to do a little bit of work. It's not completely obvious from the theorem on the previous slide, but the point is that using this computation for what happens for characters of the integers, and this theorem, you can show that you can realize all of the linear functionals up to density, all the linear, actually you can get all of them, no, up to density you can realize all linear functionals on this inverse limit of the K-theory groups of finite subcomplexes of B gamma via relative theta invariants of something. And then because now that tells you there's enough differences of flat bundles to realize everything, and by the isomorphism of little KL with the Pontryagin dual earlier, that tells you that the flat bundles are dense in the Pontryagin dual, therefore the representations are dense in little KL because it's a topological isomorphism. Sorry, I didn't explain that at all. Okay. It does take a little bit of work, but that's the idea.
Okay.
Yeah.
Thank you. Are there any further questions from the audience? Otherwise, we thank Rufus again, and I will stop the recording once I again find the appropriate button.
Okay. Yeah, thank you very much for the invitation. Good luck with the rest of the World Cup, I hope. It continues to go well.
Yeah.
Okay.
Yeah.